Okay, so this is section 1.2. Excuse me, not sure which one it is. We're talking about algebra on coordinate plane. Okay, so a lot of this is going to look familiar. First thing I want to talk about is midpoint formula. It's back. And you're asking what this is doing to college algebra. You'll see. Let's say we've got 2 points. All right, this point is going to be at 1, 1, and this point will be at 3, 2. So what the midpoint formula does, it's just going to find a point which, if you connect these with a straight line, will be in the middle. And the midpoint formula is x1 plus x2, and it gives you the x and y coordinates over 2. There's the x coordinate, and y1 plus y2 over 2. Or in other words, you're just averaging them. So we can plug in on these guys and get them. So I'm going to have 3 plus 1 over 2, and then I will have 2 plus 1 over 2. Where this is x1, y1, x2, y2. So 3 plus 2 is 4, divided by 2 gives me 2. 2 plus 1 is 3, divided by 2, I get 3 halves, or 1.5. And that is the midpoint formula. Other we're going to talk about is distance formula. And these formulas show up again in calculus. Distance formula is used to find the straight line distance between 2 points. All right, and we're going to deal with our old points again. 1, 1, 1, and 3, 2. Distance formula, it's the square root of x2 minus x1 squared plus y2 minus y1 squared. Sometimes you'll see these two terms interchanged. It's the same formula. So there's x1, y1, x2, y2. Now I plug in. So it's going to be 3 minus 1 squared plus 2 minus 1 squared. This is going to be the 2 squared plus 1 squared. It's going to be the square root of 4 plus 1, which will be the square root of 5. A little bit over 2. And that is the distance between the straight line distance between these 2 points. Okay, another skill you're going to have to learn how to do is to sketch the area or region for inequalities. So let's deal with one. They want you to sketch this region, and it's going to be x, y, such that x is greater than or equal to 3. All right, so what you do, this is really remarkably easy. yourself a coordinate grid. Now I've got to sketch an X and a Y. Otherwise, if it was just X, it would be a number line, where X is greater than 3. So I come over, here is X is 3. See, what this tells me is I'm going to be dealing with a vertical line, and because the equal, it's solid. And I'm only interested in the areas where X is bigger than 3, which is going to be off to the right. And that is how you do that one. Okay, so let's deal with one that's similar but not quite the same. Again, we want to sketch a region. And this XY tells us we're in two-dimensional space, a coordinate grid, such that X is between 1 and 2. But you notice it's not equal, it's just between those two. So again, we do the same type of thing. First thing we do, draw our number line. Alright, so I come back over X, but I'm not equal, so this is going to be a dashed line, and that's X equals 1, and then I want X equals to 2. Again, it's dashed, because they're not strictly equal, and I'm only interested in those X values between them. So the only area I shade in is between those two numbers. Okay. Here's a fact you've probably forgotten, but you're going to need. Area of a triangle is equal to 1/2 base times the height. All right? So if I give you, this is your base. Now in this case, your height is the perpendicular distance from your base to a vertex. This one lies outside, there's your height. If I give you coordinates here and here, if I give you coordinates of these, then obviously the way you find the length of your base here is to use the distance formula, and you need to do the same thing over here. Now, this X is going to be the same as these ones, and its Y will be the same as this one. And then all you have to do is plug that in and get your answer. Okay. X-intercepts. This is where we start to get into the meat of this thing. This is where your graph crosses the x-axis. These are also known as zeros or solutions, because it's where y equals 0. So x-intercepts are also sometimes called zeros or solutions, depending upon the context that we're using them in. But graphically, they're the same points. Y-intercepts, where it crosses the y-axis. So to find x-intercepts, y equals 0. To find y-intercepts, x equals 0. So why, you say? Well, all right. Let's take a look at an example here. Remember, x-intercepts are where it crosses the x-axis. So there is 1. That's my first x-intercept. And there's my second x-intercept. And you will notice that at the x-axis, the y value is equal to 0. All right. We have 1 y-intercept. It's right there. And if you take a look, it lies on the y-axis, which is where x equals to 0. And that's why you set these things equal to 0. And you're going to be finding x and y intercepts. All right, Algebra 2 review. And geometry review. Equation of a circle. H and K are the coordinates of the center of the circle. This is where the coordinate plane comes in. R is the length of the radius. All right, last thing I want to talk about then is symmetry and how you use that to graph it. Symmetry is another one of these concepts. It's very important, especially in calculus, so it can save you a lot of time and energy. There are 3 basic types of symmetry we're going to talk about. Across the x-axis. And this is where the x-axis acts like a mirror. Or the function is a mirror image on either side of it. And I'm going to draw you a picture of what one of these looks like. So there's x, there's y. Say I have a function which looks like this. I know it has symmetry across the x-axis, so I want to draw it. Well, that's not bad. It's going to be a mirror image of what this is. So it's going to come down and look like that. And there's my full function. This is across the x-axis. Okay, we're also going to deal with across the y-axis. This is just like this, except instead of the x-axis acting like a mirror, the y-axis is mirror. And again, I'll draw one here. Here's my coordinate plane. My function, what I've got is this, but I know it's symmetric across the y-axis. So now I can come back in and fill this thing back in, and I know it's going to act just like a mirror of this one. And there is what symmetry across the y-axis looks like. As you can see, it's acting like it's a mirror. Or if you folded it across the y-axis and moved these over, this would lay on top of this. Here, if you fold it across the x-axis, this would lay on top of this. Okay, the next we're going to deal with is a little bit harder. Not much, but a little bit. And it's symmetry through the origin, which you should recognize as 0, 0. Okay, so symmetry through the origin is where the equation is unchanged. When you replace x and y with negative x and negative y. Or the other way of thinking about this, the symmetry of the origin is where can rotate it 180 degrees about the origin and end up with, you can take part of your graph, rotate it 180 degrees about the origin, and you end up with the other part. So let's take a look at what this actually looks like. And I'm going to use two examples. Here's my coordinate plane. You should be able to recognize both of these. This is y equals x squared. And this is y equals x cubed. Parent function of quadratic and the other one. Okay. Now, one way to take a look at this, if you take a look at the quadratic function right here, anything which has symmetry through the origin is going to be in opposite quadrants. And this is going to act like a mirror. So if you take a look at this, this guy is not in opposite quadrants. So it is probably not going to have symmetry through the origin. The cubic, however, does, so it's a candidate for it. So let's take a look at how you do these algebraically. Y equals x squared. There's my parent function. Remember I talked here about when you replace x and y with a negative x and a negative y. That's what I'm going to do. Negative y going to equal to negative x squared. All right, now you guys should know by now, I harped on you enough, when you square a negative number, it becomes a positive. So negative y will equal x squared. It's the same thing. And if you compare this one to this one, you notice that they are definitely not the same. So this is not symmetry through the origin for a quadratic. So now let's take a look at our cubic. Y equals x cubed. This is one where we think we've got it. So we're going to do this. Negative y equals negative x cubed. All right. Negative x times the negative x. Remember, this is the same as this. So negative x times negative x gives me x squared times another one will give me a negative x cubed. All right? So remember, these give me x squared, and then I'll multiply them again by a negative x. I'm going to end up with a negative x cubed. Okay, well, you would think, well, they're not the same, but I can make them look the same by multiplying both sides by negative 1, which is going to give me y equals x cubed. And you notice I ended up with the same equation. So the cubic does have symmetry to the origin. As a matter of fact, very, very few of the even functions, ones which have an even power, are going to have symmetry through the origin. There are probably some, I just can't think of any. The odd ones, the ones where the highest power is an odd, are the ones which are most likely to have symmetry through the origin, but they're also going to have to go through the origin. So this is your next section on algebra on the coordinate plane.